Good afternoon, dear students. Today's class we are going to discuss general characteristics of the compounds of the alkaline earth metals. Generally, alkaline earth metals are dipositive compounds. Dipositive compound means plus two compounds. So, beryllium 2 plus, magnesium 2 plus. So, they are dipositive compounds. So, this dipositive compound contain 2 electrons in the valence shell, general electronic configuration Ns2, and they are less ionic compound than the alkali metals because of increasing the nuclear charge with smaller size. So general characters of this alkaline earth metals mainly explained due to the increasing nuclear charge and smaller size in this. So first we are going to see the oxides of alkaline earth metals. Oxides. Generally, oxides of alkaline earth metals prepared by treating this alkaline earth metal with oxygen, and because of the addition of this oxygen with the alkaline earth metals, they prepare oxides and peroxides and peroxides. Okay, so we have two types in oxides. First type, monoxides and peroxides. Monoxides and peroxides. Generally, monoxides are prepared by heating these metals in the presence of oxygen. So they form BeO and MgO and MgO, then BaO. Likewise, they can form the monoxide. And from this monoxide of this alkaline earth metals, beryllium oxide and magnesium oxide, that means BeO and MgO, both are BeO, beryllium oxide and magnesium oxide, both are almost, they are insoluble in water. They are insoluble in water. This is monoxide. How to form the monoxide? Treating this alkaline earth metals with with oxygen by heating. So beryllium oxide and magnesium oxide both are insoluble in water, so they can't form hydroxide, because when treating this oxide of alkaline earth metals with water, they prepare or they result in hydroxide of the particular metal. So now all the metals are in the group 2 alkaline earth metals. They form oxide and they can soluble in water. Because of the solubility of this oxide in water, they prepare hydroxide. They can prepare hydroxide, but these two are insoluble in water, so they are not preparing hydroxide easily because almost it is insoluble. Okay, then the oxides of this alkali metals have different character. Beryllium oxide is a amphoteric nature. We know that beryllium is an amphoteric nature compound, so its oxide also amphoteric in nature. And magnesium oxide, it is weak base. It is a weak basic compound. And other oxides like calcium oxide, strontium oxide and barium oxides, they are basic, that means strong base. The magnesium oxide is a weak base, the other are strong basic in nature. Beryllium oxide is an amphoteric nature and it is also a covalent nature compound. It's a covalent nature compound, beryllium oxide. So in between beryllium and oxygen we have covalent bond. So this is covalent nature compound. and other all the elements have ionic, they are ionic ones. So other elements are ionic in nature. Ionic in nature. First type monoxide over second type peroxide. So peroxides, except beryllium, other all the metal can form peroxide. So how to prepare the peroxide? Treating this monoxide with the oxygen at high temperature is prepare peroxide. So beryllium is not forming any peroxide of this peroxide, but they can form only oxide, and other all the metals can form peroxide. How they are forming the peroxide? Treating this oxide, metal oxide, with excess amount or with the oxygen at high temperature. So the equation for this, 2 moles of barium oxide combined with oxygen, or it's treating with oxygen with the heating, okay, with the heating, applying heat. So they produce peroxide. They produce peroxide. Next, hydroxide. So beryllium oxide is amphoteric in nature, and other all the compounds are basic in nature. Anyhow, magnesium oxide is also a basic in nature, but they are weakly it is weak base. But other all the elements like barium, strontium, calcium, they are strong basic. So because of this basic nature, they are sparing, they can soluble in water, and they produce hydroxide. So how to produce the hydroxide? Metal oxide combined with water. Metal oxide combined with water, except beryllium oxide. Other all the metal oxide combined with water, they produce hydroxide of the metals, of that metal. Then move from top to bottom of the group. The stability, that means thermal stability, and solubility, and the basic character. So we know that thermal stability, solubility is increasing because magnesium is less soluble compared to calcium, barium and strontium, and they are it is a weak base. When you move from top to bottom, solubility is increasing, basic character or basic nature it's also increasing, and thermal stability is also increasing, okay, as well as they are increasing. These alkaline earth metals hydroxide are less basic, and they are less stable than alkali metal hydroxide. So the alkali metal hydroxide compound, comparing with the alkaline earth metals hydroxide compound, when comparing these two are less basic and less stable than the alkaline metal hydroxide. So the alkaline earth metals are less basic and less stable than alkali metal hydroxide. So beryllium hydroxide is amphoteric in nature. They can react with acid and alkali. That means both. We can react. Beryllium can react with acid and base. For example, for this amphoteric nature of beryllium hydroxide reacting with base sodium hydroxide, they prepare here the resultant Na2BeO2 with 2 molecules of H2O. And another example for this amphoteric nature, because it is reacted with the base, you have to react this with the acid. So beryllium hydroxide reacting with acid to hydrochloric acid, and reacted, given the product is beryllium chloride, 2 molecules of H2O. This is resulting that beryllium hydroxide or beryllium reacting with can able to react with acid and base. So this character is described here. Beryllium is an amphoteric nature compound. Next, halides. Alkaline earth metals can form halide. So their general formula is MX2. Formation of halide is M plus X2 produce MX2. Metal is metal M is denoting magnesium, calcium, strontium, barium and radium. X is denoting fluorine, chlorine, bromine, iodine. The beryllium halide have some exception case in this halide formation because they are covalent in nature. They are smaller in size, Be2+. So beryllium halides are hygroscopic compound. Okay, so they can fume in the moisture air and they are soluble in the organic solvent. So what is the exception case? Beryllium is an exception case because of the smaller size and covalent nature. Small size and covalent in nature. Covalent nature. Because of that, they are hygroscopic in nature. Hygroscopic nature, and they fume in the moisture air and they soluble in the organic solvent. So halide of the beryllium is a different structure. Example, beryllium chloride has chain structure in the solid state. So in solid state they can show the chain structure. So what is the chain structure here? Solid nature, solid beryllium chloride can show the structure like this: beryllium, chlorine, chlorine, beryllium, chlorine, chlorine, beryllium, chlorine, chlorine, beryllium, chlorine, 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 chlorine. So this is the chain structure of beryllium chloride when it is present in the solid state. And when the beryllium chloride is present in the vapor base, they can show the compound like bridge structure, chloro bridge dimer structure. So what is chloro bridge dimer structure? It is present in the vapor state and showing like this chloro bridge with beryllium. Existing like this. And when the beryllium chloride is present in the linear monomer in high temperature, 1200 Kelvin, they show the compound structure like beryllium chloride, linear compound, monolinear or monomer. Except beryllium, all the alkaline earth metals are ionic in nature, and chloride, fluoride of all the metals are ionic solids, and they are the halides of the alkaline earth metals are good conductor. They can conducting the electricity easily, so they are good conductors. So they are good conductors of electricity in the fused state and also in the aqueous solution. So they have some tendency to form the halide hydrates, hydrate halides. Gradually it is decreases. For example, hydrate halide is decreasing when it is soluble in the alkaline earth metals is associated with the hydrate compound. That means with the water compound. For example, magnesium chloride with 8 water molecules, and the calcium chloride means calcium chloride compound. It is only formed with the association with the 6 water molecule. When took the strontium chloride, this is combined with the 6 water molecule, and with the barium chloride solution it is combined with the only 2 water molecule solution. So it is decreases when increasing when moving down to the modern periodic table group 2, the tendency of form halide hydrates are decreasing. Next, salt of oxo acids. Oxo acid, what are oxo acids? Carbonate, sulfate and nitrate salts is generally known as oxo acids. First, we are going to see the carbonate. All the metal carbonate, that means the alkaline metal carbonates, undergo the decomposition process by heating. They produce carbon dioxide is a byproduct, and oxide of a metal oxide is a major product. For that reaction, metal carbonate is a oxo salt. It is undergo the decomposition process by heating. They form metal oxide and releasing CO2 as a gas. It's a byproduct. They have some characters. Carbonate of alkaline earth metals. Their solubility of the solubility of carbonate in water is decreasing. In water is decreases when moving down to group. Second character, thermal stability is increasing. When moving down to the group with increase in the cationic size, that means the atomic size. Next was oxo acid, sulfate. Sulfate of alkaline earth metals are generally they are white solid and they stable in heat. Thermal stability. They have thermal stability. Thermally stable. Beryllium sulfate and magnesium sulfate are easily soluble in water. So the solubility decreases from calcium to barium sulfate, calcium sulfate to barium sulfate, it is decreases. And another character, greater hydration enthalpy of beryllium and magnesium ion, they overcome the lattice enthalpy. So the greater hydration enthalpy, so they dissolve in the water. So because of that, they overcome the lattice enthalpy factor, so their sulfate are soluble in water. So magnesium and beryllium sulfate are generally soluble in water. Next salt, nitrates. So the final oxo salt, nitrates are prepared by dissolving this carbonate into dilute nitric acid. So magnesium nitrate is crystallized out with the 6 molecule of water, you know that, and barium nitrate is crystallized out with an anhydrous salt. It is hydrated out as anhydrous salt. So this again, it show that, or it is proving that, decreasing the tendency to form the hydrate ion with increasing the size. In the nitrate also it is the same case. When increasing the size, the hydration ion formation is decreasing. The nitrates of all the alkaline earth metals, generally they decompose and they form oxides. Alkali metals are playing a important role in our life, for daily life. We use this alkali metals for many uses. So we are going to see the uses of this alkali metals for each alkali metals. First one, beryllium. Uses of beryllium. Beryllium is a rare element, and because of its low atomic number and low absorption, absorption of low X-rays, it can use this as a radiation windows. In a radiation window we use this beryllium, and for the X-ray tube and X-ray detectors. X-ray tube and detectors. For radiation window also using the same one, okay, beryllium. So you know that beryllium is absorbing, or it is a low absorption of X-ray energy. So because of this low absorption of X-ray energy, this X-ray samples are kept into the X-ray equipment. So for the X-ray equipment, for getting the analysis of X-ray values for the particular sample, we use this beryllium as a sample holder because of the low absorption of X-ray energy, low absorption of X-rays. And also beryllium is a transparent one to getting the energetic particles. So because of this specific character, we use this beryllium to build beam pipe in accelerators. First, sample holder in X-ray equipment, and the next one for beam pipe in accelerators. Next use, because of their low density and diamagnetic nature, we use this as various detectors. Next, magnesium. Uses of magnesium. Magnesium is also the important metal we use as a photo engraved plates for printing industries. printing industries. Then for the refining titanium in Kroll process, we use this magnesium. For the refinery titanium refining, that means that process is known as scroll process. We use this magnesium in scroll process. Third use, magnesium is using to remove the sulfur from iron and steel. Removing sulfur from iron and steel. Next use of magnesium. Magnesium is a ribbon used here to synthesis Grignard reagent for the organic synthesis. For synthesis, which synthesis? Grignard reagent synthesis. So in the Grignard reagent, magnesium is a major reagent to combine with the other halogens. They form Grignard reagent. So this is magnesium is using us to prepare Grignard reagent. Generally, Grignard reagent is playing the major role in the organic synthesis. Next use, it is using as a desiccant. Using magnesium as a sacrificial anode to controlling the galvanic corrosion. Galvanic corrosions. Then magnesium is combined with the aluminium to form alloy to improve the mechanical and fabrication and welding property of this magnesium. This is also the one of the use of this magnesium. And magnesium alloy, generally magnesium alloy is using as a tool in the aeroplane and missile construction. Today's topic over. Thank you, students.